Hi, everyone. Today we're going to talk about the eBPF, OpenTelemetry, and how it actually solved some of the problems within the Finastra. The title of this talk is much shorter than what you see on the agenda. That is because it just doesn't fit the slide. To start with, my name is Vladimir Babichev. I'm a platform architect at Finastra, doing all the platformy stuff, but generally speaking, building the resilient, reliable solution that underpin financial services provided by our company. I am a travel addict, a Kubernetes expert, and home enthusiast. So practically that means is that I can switch on and off lights in my home by editing YAML files by sitting somewhere in the chair. I also mastered the high availability, like 4 nines SLAs and 0 downtime deployments, because I can't really explain my kids why they have to go to sleep at 6 p.m. during the winter time.
Hi everyone, my name is Maciej. I'm an expert software engineer at Finastra. I'm a member of FFDC Poland team. Most of the time I spend traveling around the world. Here, for example, you can see a picture of myself in Bryce Canyon, USA, rendered in Pixar style, which is a proof that AI doesn't just help us developers code, but it can also help save some really bad selfies. Also keep in mind that this is my first time on stage and I'm quite nervous. Sorry if this looks more like improvisation than presentation. I'll try my best, but stay with us. I think the topic is really worth it. So before we move on, allow me to introduce the company we both work for, which is Finastra. So Finastra is one of the world's leading financial software companies, serving over 8,000 customers, including many of the top global banks. So our solution covers corporate and retail banking, payments, lending, treasury, and capital markets. So with strong focus on open platform and collaboration, we empower our clients to connect, scale, and deliver better experience for their customers. And we call that innovating finance together. FusionFabric.cloud, or FFDC in short, is Finastra's platform as a service solution. So it fosters collaboration across the financial services ecosystem by exposing Finastra core systems through Fusion Fabric Platform API. To put it simple, you can think of it as a gateway that gives you access to banking products locked within bank infrastructure, which enables fintechs, independent developers, or even students to create a wide range of innovative financial services that were previously out of reach. I have prepared some numbers to help you visualize the scale of this FFDC platform. So every day we are processing more than 2 million core banking requests. At the same time, we are handling more than 8 million internal API calls between our 20+ microservices. So with such large and distributed environment, it's really challenging to track down issues, especially when it comes to timeouts.
So have you ever faced the problems that are really difficult to understand and just understand what people want from you? So one of the biggest problems for me is always network. If somebody tells you it's not network, it's usually a network. It's always a problem when the problem you can't really reproduce, and networking is just one of those things. So a few months back, the Maciej's team, FusionFabric.cloud, reached out to us saying that they have a problem with their pipelines. Now we understand that roughly 20% of the builds at the time were failing, and yeah, we couldn't understand where it's coming from. Sometimes there were like really bad days where none of the builds were succeeding. Sometimes where just one build failed, another 5 succeeded, and it was absolutely fine. So we couldn't understand. Now looking back, we can understand that it was like actually the team was doing 4-day working week instead of like a full time. So it was good. Another, like whenever they were explaining problems, they done their obvious analysis. Like one of the things that was popping up is the connection timeout. So connection timeout is when the service A tries to talk to service B, however they fail to do so. So service B never received the connection. They also identified the problem was related to the read timeouts, It's when service A talks to service B tries to reply back, however, service A never receives the response. Again, if you are technical, you understand those are different things lie on different side of the stories. To add more to the mix, effectively, Tim mentioned that the problem is surfaced when you see like 400, 500 errors. Just on this graph, everything is orange is good, everything not orange is actually some type of error. It's kind of okay. You can see some patterns. You understand where you potentially can look at it, but there is a catch. Not every 400 or 500 error is good or bad, and some of them are actually good. So some like legitimate, right? The user authentication token failed, and so on. So how do you understand? So that was the thing. And the best thing, it was just failing in one of the environments out of 5. The worst thing, it was the integration environment where not just this team had problem and their builds were failing, but rather many other teams experienced the same problem. So who tried to integrate with the Fusion Fabric.cloud, use the APIs and so on. And you know where it leads to. It kind of fingers pointing in your direction saying, well, you better fix it because it works everywhere else. You know the stories where you have a patient come into GP, right? They are very well known about like what their problem is, how to address it. So they explain their symptoms and effectively expecting the doctor to write prescriptions exactly what they want. But instead, doctor gives them just paracetamol. And that is just simply because doctor needs time just to digest. Like, is this guy actually knowing what he's talking about? Is this the real stuff or not? And we needed the same stuff. We thought we actually have this pill. We, as the platform, we implemented 3 pillars of the observability, so metric, logs, and traces, as the service a long time ago. The caveat, though, team didn't use it. That is because they were so mature. They were very good in terms of their tracking down problems with their systems, and they usually don't have any problems in their production environments. And even if they do, their MTTRs are quite low. So they never really looked in what that platform team provides. And that was our first learning. If you do your observability, track adoption. Because without that, there is no guarantee that people actually, you provide any value to them. So we were actually stuck. We were scratching our heads. Now, in order to get any insights about why this application is failing, we had to go ahead and rebuild every single application, make sure we add the tracing annotations, we add the metric exposures to the code. That would take us time. But the problem is here now, right? The 1 day out of 5, the people are gone. So we looked for the options, and we realized, well, first of all, Grafana Labs provide like a fantastic open source solution, which is the Grafana Beyla. If you're not aware what it is, it's the eBPF profiler that auto-instruments your tool. Long story short, like why it is beneficial to you, because it gives the basic tracing, so you can understand which application talks to which, very important in the microservice distributed world. And on top of that, it provides the read metrics. So requests, errors, and duration. Kind of the basics about how you should observe your environments. And that was fantastic. That was actually our paracetamol, because that was a silver bullet that we thought they will fix all our problems. We got the service map. Like, we have a clear understanding what is what, who is talking to who, how the applications behave, which of them are failing. We had the real-time service map. We could go back in time and understand, like, at that specific moment, who talked to who, not just relying on the knowledge that was passed between different engineers or documented. And sometimes, you know, the documentation can be outdated. And we got the standard metrics, right? So this is the example of the dashboard that you can download from importing your Grafana Cloud instance from the Grafana Cloud Marketplace. And what is important, you have the same set of metrics irrespective of the language your application is written on. So that's Node.js, that would be Java, that would be Golang, whatever that is. Suddenly your teams talk the same language. They observe the applications, same level. What we also expected from this, we expected to get tracing, understand how we can trace the actual requests that are like passing through the system. But unfortunately, it didn't work for us. We faced the problem where the Beyla faced the issue with the context propagation and didn't work. Well, it gave us some input, so with the team started investigating, we started understanding like what happened there, but we kept looking. So the next thing on our list was the OpenTelemetry. So it's a common thing now, everybody talking about OpenTelemetry these days, but it's a collection of APIs and SDKs and tools. They help you to instrument your applications and get metrics, logs, and traces. So same thing over and over again. The reason why we didn't look in OpenTelemetry in the first place is that word APIs and SDKs. When we thought about it, we actually considered, well, probably it's the same stuff as Prometheus and Tempo with the tracing. We have to rebuild our applications and check those annotations and have things happening. And we just push it back. But time came, we read the documentation, they have massive documentation. If you go in there, it's just really, really difficult. But we were surprised that it took us like maybe 2 pages to read, and they support auto-instrumentation. So in order to get all the microservices that were facing the problem, we just needed to create one manifest inside of the Kubernetes, restart our applications, and we suddenly were getting same red metrics, like in a much nicer view. So this is application observability service provided by Grafana Labs. We got more drill downs into the system, so we can understand which specific parts, how they're behaving, etc. And we got tracing. We finally got that context propagation, understanding here is the traffic coming in request coming into the system. This is the ingress controller, this is microservice A, microservice B, how it talks to the database, and so on. And the cherry on the cake, we were able to see not just the service map between different components, but we could see the request flow. So pinpoint to the exact functions in the code that was responsible for processing that request. And that's where we got real traction.
Okay, so now I'll show you a couple of examples, 2 actually, that observability helped us to solve. So as a dev team, we've been trying to track down which services are getting those timeouts, but in this distributed environment, it was not that easy. But with all the observability deployed by Vladimir and his team, with 0 code from our side, we're able to narrow down one of them, and it happened to be lack of proper timeout configuration. So with Grafana Tempo Enable, we're able to see this beautiful request span graph. It's not that beautiful here because I had to blur down some internal implementation, but you get the point. What we can see here is that the initial request times out after 5 seconds, which is OK, because that's the configuration we use for the client, which is API gateway in that case. However, requests to underlying services, those ones marked with green, kept going, some of them for a couple of seconds, and some of them even for a couple of minutes. So such requests have 0 chance of success, because by the time the response arrives, the connection is already closed. So it's like wasted resources. And those long-running requests led us to exhausting pool of threads, which were able to handle incoming requests. So what was the result of it? The environment was completely frozen. And Grafana Tempo includes class name and method name in the Java code. So we're able to pinpoint exact point in code where we need to place the fix. As for the fix itself, all I had to do was to add timeout to our Spring Boot implementation. And with this setting, the requests, long-running requests, were terminated, and there were no more dangling connections. So just simple 2-liner helped us increase the stability of the environment. However, after some time, we kept getting another issue, but again, observability helped us to identify and fix it. I'm talking about the cache Stampede. So what is this? It's basically a performance issue that occurs when multiple processes simultaneously attempt to regenerate missing cache entry. As a result, each thread performs expensive operation independently, overwhelming the underlying resource with redundant requests. So underlying resource can be like database and some operation can be like large query to read the data. In the examples I have prepared for you, we'll consider two kinds of endpoints, JWKS and token endpoints. So basically, the token is, as it says, it's used to get the token, and JWKS is used to fetch the JSON web key set, which is basically set of public keys required to sign the token. I marked them with different arrows, so you can distinguish them. What is important to mention is that those endpoints are used both by our customers and our microservices. So when the first request comes, it's immediately served from the cache. We get the response. We get another. Then, in the meantime, we can get some authentication request. Response is quickly served. Same for the other one. Everything is working fine. What is important here is none of the JWKS requests touches the database. Everything is served from the cache. So now the scenario with invalidated cache value. To simplify, let's assume that connection pool of our database is free, so we can handle only 3 connections at a time, okay? So the request comes, the cache is expired, so request tries to regenerate it, calling the key cloud first and then the database. When another request comes, it does exactly the same. It also tries to regenerate the missing value. In the meantime, we have some token request, which also takes one of the connection from the pool, which is now fully depleted. So even though those database requests will eventually finish, we end up with pile of stacked requests. And you know what the result is? Yep, environment is frozen again. So deploying observability allowed us to get some proper threat metrics. Here we can see pool of HTTP workers, which has been exhausted due to overwhelming number of requests. So all of those threads are in blocked state, which means they are basically queued up waiting for some executor. We could just increase the number of threads, but that would cost us more resources, basically, and would also conceal the actual root cause instead of fixing it. So we decided to keep digging. We looked into other kind of metrics, which is database connection metrics. You can see on this slide that the number of connections spikes up abruptly. Then it's on the top for around 30 minutes, and then it goes back to normal. And why it goes back to normal? It's because our friend Kubernetes, which comes with the health check and keeps restarting the services until it gets back to operating state. What is funny, we noticed that this situation is happening almost every 24 hours. We've had an impression that there must be some time-based event which is running like some pipelines, some job in the cluster, whatever. But it happened roughly every 24 hours. I did some code analysis, and I found that we are using cache that is regenerating the value every 24 hours. So the fix is simple. It's adding this sync set to true within the cacheable annotation. So simple thing, but to implement it, you need to find the root cause. Okay. And then how it works with proper sync mechanism. The cache entry is expired, so as in previous example, it tries to regenerate it. Other requests are kept at the token service level, waiting for the value to be regenerated. In the meantime, we can have some token requests which are not blocked anymore. Everything is working correctly, and all of this thanks to observability.
Thank you, Maciej. So what has changed after we resolved the problem is we learned our lesson as a platform team that observability should be useful. This is, for example, our current stack, or not current, the past stack before the problem. It's very standard. You have dedicated metrics instances that are running in HA mode. You have the traces instances, and you have logs. What is important from our platform perspective that we run multi-tenant Kubernetes clusters. So you have different product teams deploying their products on the same cluster, and they're sending data to their dedicated Grafana Cloud stacks. So we need to make sure we have this flexibility instead of merging everything together. It kind of works fine, apart of the situations where we have dedicated nodes running for Prometheus or Grafana Agent or Alloy, just capturing all the data, and then it becomes very costly. So what has changed with this analysis, what we've done? First of all, we delayed our migration to Alloy, where we're using Grafana Agent. And what we learned with the Alloy, that you can actually deploy it and it will do everything for you. So it's like Uber application. It does your OpenTelemetry, metrics, logs, traces, just in one box. It also can do Beyla. It can also do profiling. Just fantastic. So what we do, instead of having, again, dedicated alloys for metrics and so on, one agent does everything. So it serves all the ports within the same node and capture all the information. This way, it helps us to isolate our failure domains, making sure we have more stable environment, and we also reduced our memory footprint. So we no longer have this problem, why our Prometheus consuming 30 gig of memory, and we investigated, or probably one of the teams have added some extra data. It was all good until when we came into the point trying to platformize it and get it running. So the problem that we faced with Alloy and running it in Uber mode was the configuration. It was 800 lines of code just for one product, and we have 5 of them, for example, deployed on the cluster. So it's kind of good, right? You put it in place, it's just working there. The trouble is the maintenance. How do you do your day-to-day operations? How you introduce a change, and etc. So we looked a little bit into a thing, and the way how we cook our systems is we deploy it through the Helm charts. And what is important, we package all the components related to the system within that environment definition Helm chart. So in our case, we distributed the Alloy configuration into multiple chunks. So the Alloy itself, the Helm chart for Alloy deploys the main core components of the configuration. And then any product-specific configurations, they are deployed in their respective namespaces, just over here on the top and somewhere on the bottom. And that way, you have this more granular control, who does what and how do you do. Then to manage all these things together, we use the mutating webhook controller, like in this case, we use Grafana, that will actually read the configuration from the different products environments, Alloy configuration itself, merge it into the one Uber configuration file, and then the Alloy will watch for any changes into that config map, digest it, reload, and will implement things. So what did we learn from this thing? First of all, I guess the most important question, why was it the problem just in one environment? Why it wasn't in production? Why it wasn't dev? The answer is very simple. We've been over-provisioned. We were 4 or 5 times big instances that we needed. And that's why the problem was never faced, and the requests were processed much faster. But what also we did, we prevented the effectively denial of service in the actual production environments, and we unblocked our pipeline. So the teams got back to the normal 5 working day week. Probably we shouldn't have done it, actually, but whatever. We learned that we can do the zero-code observability, and that is extremely powerful. So instead of working with every single developer team and chasing them and educating them, oh, this is the observability, this is how you do it, this is the standards, and so on, we actually shifted it to the left, and we own the entire stack. So if the team wants to add anything else to their default setup, they are more than welcome to do it. They just need to learn it. But if they don't, they get the standard set of metrics. And then suddenly you have the same common language spoken by different teams in different geographies in different continents. They have read, they have traces in place, and it costs them absolutely zero to do. As I mentioned, standard metrics dashboards. what is important, we got the service and request maps. There are no more spaghetti balls. It's just very clear understanding what's coming, where it is, etc. We empowered our team. There is no more finger pointing, like, this is not my thing, especially with the remote working, and it's very common in our company. You get people to the same table, and instead of being a problem owners, we became the solution providers. That was very powerful for us. We obviously improved the resilience and scalability for our solution, so we reduced the cost of ownership for our Alloy deployments, and we learned our lesson. We improving the way how we tracking the adoption of the services by different teams. Thank you very much.